Okay, thank you very much. Yeah, so I want to tell you about two enumerative geometry problems. So curve counting. And the two problems, one will be on Abelian surfaces. And the other will be on an Abelian threefold. And you can find these, there's a paper by this title, and let me just, on the archive, so this is all joint work with George Oberdiek, Rahul Pandey, and Qizheng Yin. And so normally I don't like to talk about, it's really two problems, but I'd rather just talk about one problem. But the two problems, both the question, they're at least superficially related. One's on Abelian surfaces, one's on Abelian threefolds. And their answer sort of strangely ends up being given by the same function, which is a Jacobi form. And so I want to actually, this main point of this talk is going to be geometry, is going to be about the enumerative geometry. But since the answer to these two problems comes out in the same, as basically the same Jacobi form, I want to start off with that and tell you about this Jacobi form. So we'll start here. So this is just, it's going to be a two-variable power series. So let me, actually I want to put it somewhere where we can keep it. Maybe I'll put it here. I want to write it big enough so people can see it. So let's put it equals P. Okay, so this, for the purposes of the geometry, this is going to be, I'm going to use this mostly as a formal power series, but it's worth noting that this is this is a very special function. If I think of P and Q, the power series in P and Q is giving me Fourier expansions, so I'll write P as exp of 2 pi I z, and Q as exp of 2 pi I tau. Then of course I can think of z and tau as well. Z is a coordinate on C, and tau as giving me an elliptic curve. Given by quotienting C by that lattice. So a point Z and a point tau give me a point on the universal curve over the moduli space of curves. So Z tau give a point on universal elliptic curve. And of course, Jacobi forms satisfy some symmetry relations with respect to the action of SL2Z and the action of this lattice on Z and on tau. And so as an algebraic geometer, I like to think of this as giving me a section of a line bundle over the universal curve. Let's see if I can manage this here. Okay, so KPQ is a Jacobi form, i.e., this one might be meromorphic, section of a line bundle on the universal curve. And this Jacobi form has index 1/2 and weight -1. So K. And which basically give us the degree of this line bundle over the fiber and over the universal section. Okay, so I mean, the fact that this thing is this nice arithmetic object, for us, for the geometry, it's a bit of a coincidence. Like, I don't really, the fact that it has this beautiful property is not going to be seen directly from the geometry. It'll be this kind of amazing coincidence. For us, the important point, this is just going to be a formal power series. Let's in fact examine what it is. Formally, note that, in fact, I'm only going to use even powers of this. So if I take an even power of it, the square roots go away. And what do we see? If we expand this as a formal power series in Q, the coefficients are actually are Laurent polynomials in P, right? So this thing and everything has integer coefficients. Sorry, what? Thank you. Yeah, so you know, I think k to the even power, I think, might be here. Some of these, it might be a section of either an orbital line bundle or maybe a cover. So, yeah, in particular because of the weight 1/2. But I'm only going to use even powers. So formal power series in Q, whose coefficients are Laurent polynomials, right? We can just look at that. And you can also see that it's a symmetric. The coefficients here are palindromic Laurent polynomials. So they're invariant under P goes to P inverse. Okay. All right, so now to the geometry. So this is going to, this object for us is going to be a generating function that gives us solutions to our geometric problems. Okay, so let's formulate a counting problem, an enumerative geometry problem on an abelian surface. So I'm going to let AD be a generic abelian surface with a polarization of type 1D, and so there's a corresponding curve class that I'll call beta D. Beta D be the corresponding curve class. And let's note that I'm on a surface, I've got a curve class, I can take its square. In particular, this is 2D. square is 2D. And so here's a fact that I need. I'll put it here. So I want to count curves of genus G that have in this class beta D. So a not too difficult fact is that curves, let me say the space of curves, of geometric genus I mean, of course, the arithmetic genus is determined by the adjunction formula, but the geometric genus can vary in the class beta D has dimension G. But there's part of that is there's at least two dimensions that I get just by translating a curve by the abelian surface. The abelian surface is, of course, a group. We can translate it. So I'm interested in counting curves up to translation. I'll just call two curves equivalent if they're translates of each other. So up to translation. No, I'm fixing this class, and the class is the one coming from this polarization. Okay, so just one class, and it's a primitive class. There's no, it doesn't have, there's no, yeah, they're all irreducible. So up to translation, the space has genus at dimension G minus 2. And since it has G minus 2, if we want to count something, we need to impose G minus 2 constraints. It's empty for G. So, yeah. Yeah, so it's a generic abelian surface. Yeah, so the empty set has every dimension, including -1. Yeah. Yeah, so okay, so up to translation, of course, we have a G minus 2 dimensional space. So up to dimension is G minus 2. So I want to impose G minus 2 conditions. Well, this is actual dimension. So I'm on a generic abelian surface. It's actually not too hard to see that this is actual dimension here. Conditions. Yeah, so we're going to see when I do abelian threefolds, my curve counting is going to be a virtual count. For abelian surfaces, I'm going to do an honest count. I'm going to be an honest geometer here. So I'm going to I want to impose G minus 2 conditions on my curves to get a counting problem. Okay, so G minus 2 conditions on curves. If I'm in the moduli space of curves, yeah, so for a given D, no. For a given D, so for a given D, I get an arithmetic genus determined by D. I guess it's D plus 1. And then, of course, I can get all lower genus below it. So these are like Savary varieties. So I've got some linear system. Of course, I've also got a bunch of different line bundles in that same class. And then inside of that linear system, I have the locus of geometric curves with singularities. So you should think these are going to have singularities. The interesting ones to count will have singularities. Yes. Yeah. You will. The fact that we're going to get polynomials as our coefficients, you'll see this. Yeah. That's right. So the arithmetic genus. So genus arithmetic of beta D is probably D plus 1. Okay. Yeah?
So in the fact that multiply for G with G less or equal than G plus 1. So if non-empty, it has
Yeah, I mean, really, negative dimension, yeah, the empty set has any dimension. I'm gonna stand by that convention. It's a manifold of any dimension, including negative dimension. All right.
But then probably you should say that for this values for genus, it is non-empty.
Well, we're going to see it's not empty because I'm going to get a counting problem here, right? So, okay. All right. So I want to impose G minus 2 conditions on a curve, right? So there's a really natural way to do this. You may recognize the hyperelliptic locus has codimension exactly this G minus 2 in the moduli space of curves. Right, so hyperelliptic, this is 3G minus 3, and this is 2G plus 2 minus 3. So this is exactly this codimension. So asking a curve to be hyperelliptic is like imposing G minus 2 conditions. So in fact, under this assumption that the Abelian surface here is generic, this is a well-defined, turns out this is well-defined counting problem, a finite problem. So let's define the number, n G D. This is going to be the number of hyperelliptic curves of geometric G in this class up to translation. Number of curves so up to translation of genus G, geometric genus G. In the class beta D. And I guess part of the definition is the assertion that we're going to see that this doesn't depend on the particular Abelian surface, but only the numbers G and D. Okay, so this is some integer that I would like to compute. Okay, so where should I put it? Yeah, so that's an old theorem. Yeah, so Kohn and Lung and myself did that. And that also fits into the Gutsche conjecture. So imposing point conditions is on surfaces and counting curves of genus G in a class with point conditions is kind of this old story going back to, well, Yao, Zaslow, Gutsche has been proven. So this is a slightly different way of imposing conditions. This hyperelliptic count. Yeah. Okay, so what's the answer? Okay, so if I sum these into a generating function, so I'm going to sum over G and D, number of hyperelliptic curves, genus G in this class D. And now, yeah, so just sum in a slightly funny looking way. 2g plus 2. Notice that's the number of Weierstrass points on a hyperelliptic curve. It's a stupid sign. And q to the d. Okay, here's the answer. So there's this k. I raise it to an even power. This is now a formal power series in Q, okay, whose coefficients are palindromic Laurent polynomials in P, right? Okay, so this funny sum here, these are all palindromic polynomials, Laurent polynomials in P. And in fact, this collection of polynomials here forms a basis for the Laurent polynomials. So if you want to know the answer to some given g and d, I look at the coefficient in this thing of q to the d, that's a Laurent polynomial. I write in terms of these bases, and those coefficients are exactly those guys there. This may look a little peculiar and unnatural. Maybe it's worth remarking that if I write it in terms of that coordinate on the universal elliptic curve, so this is actually 2 sine pi z to the 2g plus 2. So one way you can think of it is writing it as a polynomial in sine. If you do this guy, you can also view, instead of p, you could view these coefficients as being polynomials in sine. Okay, and that's what this is. Okay, so there's the answer. What's the geometry behind this? What's at least the idea here? So there's actually some very pretty geometry. The study of hyperelliptic curves, or counting hyperelliptic curves, goes back to the thesis of Tom Graeber, who studied this problem on P2. So the following construction is due to him originally. So the following way to access hyperelliptic curves. Oh, sorry, I was going to do one example here just to help you parse this. So for example, there's no genus 1 curves. So if you go through it, you figure out, you can see that there's no genus 1, partly just the leading, this starts with like that thing to the 4th. So no genus 0 or 1 terms. Actually, it's not strictly true. D equals 0 is sort of not really a case, because 1, 0 is not a polarization. But this all makes sense for D equals 0, and so we should define, there's sort of one boundary case, which is D equals 0, G equals 1, and is the only coefficient, so we could just define it to be that to make this work. And then everything makes sense for D equals 0. But classical examples, of course, every genus 2 curve is hyperelliptic. So when genus is 2, this is just the number of genus 2 curves in this class. And that's actually, that predates Goethe and Yao-Zazel and all of that. So if I look at N2D hyperelliptic curves, that's of course just the number of genus 2 curves. That is the sum of divisors of D. And that's a result of Debar. So that you can do by sort of counting lattices. That's a genus 2 curve. So that's fun to go and check that, by the way, if you're bored and you like generating functions. Okay, so let me give you the idea, the geometry behind the proof here. The idea, because it's sort of some pretty geometry. So if I have a hyperelliptic curve on my Abelian surface, what does it mean for a singular curve to be, hyperelliptic? Well, it means that it's normalization. So if I take its normalization, let me call the map of the normalization to the Abelian surface F, then this thing is a smooth curve which is now hyperelliptic, so it has a double cover of P1, right? And I can combine these two things to give a map to P1 across my abelian surface. And so the image of this map is a family. You can think of this now as a family of subschemes of A parameterized by P1. This image is flat over P1. So gives a family of length 2 subschemes of A. Okay, so what we see is that to every hyperelliptic, okay, I have to figure this out. To every hyperelliptic curve, I can associate a map of P1 into the Hilbert scheme of 2 points on the elliptic curve. Okay, so to each, what did we just get? To each hyperelliptic curve, we get a map of P1 into the Hilbert scheme of 2 points on this abelian variety. Now, the Hilbert scheme of 2 points on abelian variety has a map to the abelian variety. Just because take the 2 points, take the subscheme, you can regard it as 2 points with multiplicity, or you get a map to the symmetric product, and then you can add those 2 points. Okay, so, and this is of course smooth, and it's a smooth fibration over A, and because there are no rational curves on an abelian variety, this composition here has to be constant. In other words, these rational curves have to land in the fibers. And we were only interested in counting hyperelliptic curves up to translation. So by a translation, you can arrange that this map actually lands over 0. So up to translation, or using a translation, we can assume that that P1 lives over 0. And the fiber over 0 of this map is the Kummer K3. So in other words, we get a map from P1 to the fiber, which is the Kummer K3 surface associated to A, which of course everyone knows you take the abelian surface, you divide it by the action of -1. That has 16 singularities corresponding to the 2 torsion points, which you can blow up, and you get a smooth K3 surface. And so what we find is a dictionary between hyperelliptic curves on the abelian surface and rational curves on the Kummer K3. Okay, so we've reduced this problem to studying rational curves on a Kummer K3. So let's write that again. So I have hyperelliptic curves on A of genus G class beta D, and these correspond to rational curves and where the class, you have to work through this construction, depends on both beta D and G. Say it again.
Rational curves should be irreducible.
Yeah, so it's not all, this is a very important point. We're not going to see all rational curves on this Kummer K3. This Kummer K3 is a rather non-generic K3 surface. Its Picard number is very large, and so there's a lot of rational curves. In particular, these 16 exceptional curves are all rational curves. So that's part of the point. Let's see, so maybe come over here. Yeah, so what do we know about rational curves on the K3 surface? Well, as I alluded to a little bit earlier, the Yau-Zaslow formula it tells us about rational curves on K3 surfaces. The original Yau-Zaslow formula, and it's usually for generic K3 surfaces, but in fact, there's the version in Gromov-Witten theory works for any K3 surface, including this one. So the Yau-Zaslow formula tells us about the reduced genus 0 Gromov-Witten invariance of any K3 surface, including this Kummer. Okay, so there is a formula for the genus 0 invariance, and the genus 0 invariance are going to count rational curves, but in a situation like this where there's many components of rational curves, it can also count maps from a tree of rational curves, stable maps of genus 0. So, maybe I'll put it here. So what's the picture? The picture is something like this. So if I take my abelian surface and I quotient it by plus or minus 1, I get 16 rational double points. And when I blow it up, I get, there's these 16 exceptional curves. One of these honest hyperelliptic curves over in the abelian surface will give rise to an irreducible curve, which obviously does not contain any of the exceptional components, so some curve over here. So this is curve corresponding to hyperelliptic curve. And in fact, there's a converse. Any irreducible curve which is not exceptional will come from a hyperelliptic curve. So what I can do is I can use the Yau-Zaslow formula. It will tell me how to count rational curves, which will look like this, plus possibly covers of these exceptional curves. And so if you work through how to undo these contributions of covers of these rational curves in the Gromov-Witten theory, so relating, you can figure out how to relate these Gromov-Witten counts to this hyperelliptic count. So relating the Gromov-Witten count on the Kummer to the hyperelliptic count that leads to this left-hand side of the formula. So the reason for this peculiar kind of sum end right here is that exactly undoes all these multiple covers. So that this thing now on this side is really more of the Gromov-Witten type count. And then I need to sort of translate between the class I get, the variables over there, and the variables on the K3, and use the Yau-Zaslow formula. So Yau-Zaslow formula plus theta function identities give the right-hand side. Okay, so the Jacobi form comes from a combination of the Yau-Zaslow formula, which is a modular form, and repackaging it in terms of this data, so it uses some theta function identities. And then again, the left-hand side is what undoes this sort of virtual count that the Yau-Zaslow formula does on the Gromov-Witten side. Okay. So that's a quick sketch of the problem for the surface. I'd like to move on to the problem for the threefolds.
So is this an honest count?
This is an honest count. Okay. In full disclosure, there is a genericity condition that should be true. It's a little technical to state. That should be true for generic abelian surfaces by a dimension count that we can only prove in genus 3, but it should be true. So this should be an honest number, but there is sort of a genericity condition that we don't completely know how to do. Yeah. They're integers, yeah, for sure. Well, and the other thing you can do is, so the Debar calculation, genus 3, for example, you can do, or genus 2, you can do the genus 3 calculation with a lattice calculation as well, and that varies. So that checks out.
And is there a similar formula for genus 3? Like this sum of, right?
Yeah, that's what I just said. So it's a little more complicated. It's got, but yeah, it also looks like it has sums of divisors. It's more like cubic in a couple of the terms here. It's got a double sum. They all sort of look like that. That's also a fun exercise to extract genus 3 out of that thing. Okay. All right, so let's move on to abelian threefolds. All right, since A was the name of my surface, let me use a different letter for the threefold. We'll call it XD, be an abelian threefold with a curve class beta D. So it's a curve class, and I'll ask it to be dual to a polarization of type 1, 1D. Okay. Again, I want to count curves of genus G in this class, beta D. Okay, so as before, let's look at dimension of curves. Well, so the virtual, an abelian threefold is a Clabiow threefold, and the virtual dimension of genus G curves in the class beta D is always 0. Okay, so this is Clabiow 3 phenomenon. But of course, curves do come in families. So now we're in a situation where we need a virtual count. That's the one. Well, I'm going to get there. Yeah, that's. So, right, okay, so doing virtual counts of curves on Clabiow threefolds, this subject's like 20 years old or something by now. We know many ways to do that, Gromov-Witten theory, Donaldson-Thomas theory. Let me remind you of sort of the current way you might do this in Donaldson-Thomas invariants. So, Donaldson-Thomas invariant of any Clabiow threefold X is defined as follows. well, this is really a theorem of Chi-Barron, but let me just give it as a definition. We can take the Euler characteristic of the Hilbert scheme of curves weighted by the Barron function. So what is this? The Hilbert scheme is just the most naive way to parameterize curves, namely view curves as subschemes of X, where the underlying curve cycle is given by the class beta, and the holomorphic Euler characteristic is like n. So of course, instead of genus, we're going to replace genus with the holomorphic Euler characteristic of the associated subscheme. And the Barron function is, well, it's a function that is defined for any scheme over C. It's a constructible function. So it's level sets. So here's the level sets. The level sets are strata. And I just want to compute the topological Euler characteristic where I weight each strata by k, okay, by the value of the Barron function. That's all that says. So, you know, it's very close to the most naive kind of generalization of counting a finite set that you could think of. If I had a finite set of curves, right, if this Hilbert scheme happens to be finite, so I'm really counting some set of curves, then of course the Euler characteristic is just the number of points, and maybe the most naive generalization of counting a finite set to a space is by taking the Euler characteristic, and that's almost exactly the right thing to do. But to take into account some non-reduced structure and singularities, this Barron function does the trick. And what's the theorem? The theorem is that these are in fact deformation invariant. The Barron function is defined by Chi-Barron. It's, yeah. Let's just say it only depends, it's defined for any scheme, and it depends only formally locally at each point, on the neighborhood each point. It's something that tells you about the singularities in the non-reduced structure, but I'm not going to actually define it for you. So, of course, the theorem is the dtn beta of x is deformation invariant. So it really is, that's why we call it an invariant. Okay, so now let's go back to my Abelian threefold. So for this Abelian threefold, dtn beta of the Abelian threefold is always equal to 0. So it's not very interesting. It's true that the generating function is a Jacobi form, but the 0 Jacobi form is not a very interesting Jacobi form. So this is kind of bad news. It's 0 for two reasons. And you really only need one reason to be 0, but I'm going to give you both reasons. So one is that it's an Euler characteristic of the Hilbert scheme, and it's an abelian variety. It acts on itself, axon Hilb A without fixed points freely. A is sorry is X. Thank you. A is going to be something else soon. So. And if you're computing the Euler characteristic of something with a free action of abelian variety, that implies the Euler characteristic is 0. And in fact, the weighted Euler characteristic as well. Okay, so one reason it's 0 is it has a free action by an abelian variety. Another reason is I told you this was deformation invariant, and XD has deformations which make this class non-algebraic. I can deform my abelian threefold so that this 1, 1 or 2, 2 class is no longer PP. Okay, so really I've got these two problems. Which one am I going to bring down? And the reason I went ahead and gave you two reasons for why something could be 0 is I'm going to solve them simultaneously. I'm going to get rid of both problems simultaneously. Okay, so let's solve both problems at once. So we'll define a reduced Donaldson-Thomas invariant. So I'll give it a different font here, and beta A x. Well, it's got this free action, so I could just quotient by the free action. It turns out that's still a scheme. It has a Barron function, and so now I can take the Euler characteristic of the Barron function on this quotient. I've used up the quotient, and in fact, this thing now, this is deformation invariant. So it's invariant under deformations, which leave this beta D algebraic. So you restrict yourselves to the deformations that preserve the PP type of beta D, and this thing is now deformation invariant. So, for those of you sort of derived sort of people, secretly what's going on here, the reason why this theorem works, is that the Hilbert scheme, so any moduli space on Claviau threefolds has these very nice derived structure, and give them as a -1 symplectic structure. And the deformations, so one reflection of that is that the deformations are dual to the obstructions. And so we have one deformation, which is just well, we have sort of three deformations, which are the infinitesimal action of the Abelian variety on the Hilbert scheme. And those guys are dual exactly to those obstructions to deforming the curve to something that's not algebraic. And so, in fact, this quotient right here is actually a Hamiltonian quotient for the -1 symplectic structure. So normally you expect to see a moment map, right? When you do a symplectic, you normally take the zeros of the moment map and then you quotient. In this case, because of this shifted business, the -1, the moment map only affects the non-classical part, the part of the higher derived structure, the obstructions, and the quotient acts here. Okay, so this quotient is again a -1 symplectic manifold, and has this symmetric obstruction theory.
So, but this is in the derived level.
As a derived, this is a -1 symplectic manifold. It has a derived structure, but we don't need it. It's this. This is it. All right. So what's the theorem? Okay. Let's see. Maybe the theorem goes. These boards are kind of tricky to. So this is also in that BPOI paper. So if I take the generating function, D, of of these invariants. And so I'll put p minus p to the n, q to the d. So much more straightforward generating function this time. I get minus k p q squared. So instead of to the fourth, this time I get squared. Okay, so as you can see, the answers to these two enumerative problems are very similar. I mean, one was basically a k to the fourth, this one's a k squared. The two problems themselves, while superficially similar, counting curves on abelian varieties, in details it's quite distinct. One, the abelian surface case was really more honestly enumerative. It was about the Gromov-Witten theory of the associated Kummer. This one is more virtual. It's really about the Hilbert schemes of the Donaldson-Thomas theory of this x. And so the fact that they come out to being the same, roughly the same answer is frankly a mystery. And in fact, the fact that these guys have this kind of arithmetic Jacobi property is also a mystery. No idea exactly why that happens. Let me show you what goes in. I can at least show you, or maybe hint at where the Jacobi comes from in the proof here. So let's give kind of the idea of the proof. I'm going to need more board space.
Is it clear that the left-hand side is polynomial in P?
Well, that's a general property of Donaldson-Thomas invariants that is, for the non-reduced invariant, so this is this kind of reduced flavor, but for the non-reduced flavor, it's a reflection of Serre duality for the associated sheaves. So it was proven by Bridgeland, but it's difficult. So one way to process that thought is that the famous MNOP conjecture, which relates Donaldson-Thomas invariants to Gromov-Witten theory, you need that kind of symmetry in P in order to even just make the change of variables in the MNOP conjecture. So that's something that has, that kind of rationality, I mean, here they're actually palindromic. In general, they're rational functions invariant under P goes to minus P. And that sort of has a long history in this subject. So yeah, that's an important part of the story. Okay, so let me just give the idea of the proof here. So we can use deformation invariance. We can assume that our xd is in fact a product of an abelian variety and an abelian surface and an elliptic curve, okay, where A has a 1,1 polarization. So in particular, there's a curve unique up to translation, a genus 2 curve inside of it. So C genus 2 unique curve, smooth curve. And to get this class beta D, then I can take D copies in the elliptic curve direction. So okay, so we can let beta D be the class of this curve in the abelian surface, right, cross a point, plus D times the class of the elliptic curve cross a point. So what's the picture here? I've got this abelian surface, A, cross this elliptic curve. Here's E. And up to translation, well, the curve, there's going to be a curve which projects onto this C. So up to translation, in fact, I can assume that all the curves look like this. So there's this unique curve, unique up to translation. And then there's a bunch of, then there's D horizontal curves, so D horizontal curves like this. And in fact, in this geometry, there's nothing diagonal. Everything looks exactly like this. Of course, they could be disjoint from that. And because we're considering subschemes, and because D is arbitrary here, I can also have nilpotent thickenings along these curves. And because these are curves in three spaces, of course, that nilpotent thickening can be very complicated. It can twist as you go around that. So we have this kind of thing. And then, because I'm considering subschemes, there might also be just, it doesn't have to be uniform dimension. There can be dimension 0 components, so points possibly thickened floating around. And there can, of course, even be embedded points here. Okay, so all subschemes. So, I mean, what's the thought here is that the curve support the actual curve support is easy to understand in this geometry. All the complications of the Hilbert scheme come from non-reduced, from nilpotent possibilities, okay? So it's true that Hilb x mod x is still very complicated, but not so much because I don't understand the curves, but more in that you can really have these kinds of arbitrary thickenings at embedded points, okay? So all right, I have 5 minutes. I'm just going to write the sketch, just the outline of the method here. Okay, so I'm computing an Euler characteristic, right? Here's the definition. And the nice thing about Euler characteristics is they behave motifically. You can compute Euler characteristics by computing them along strata. Okay, so we want to compute the Euler characteristic using motivic and toric methods. So motivic meaning that I can stratify this space and compute strata by strata. Toric, well, we've already seen that if I can construct actions of groups, then you can restrict to the fixed points of the action. Euler characteristics of spaces with actions localize. So let me outline the basic strategy, and that's where we'll stop. So this strategy is due to myself and Martin Kuhl, earlier paper. So what's the strategy? So one, we're going to start by stratifying So because I understand all the curve support, I have this kind of natural stratification here, which is by fixing the curve support. So the various strata have maps to symmetric products of this one curve C and sim A minus C. So, for example, if I stratify by the location and multiplicities of those horizontal pieces there, you see that those strata give me maps to the symmetric product on the curve for those things that are attached to the curve, and the symmetric product of A minus C. The other parts, and I'm going to compute. For this stratification, yes, that's going to be separate. And I can look at the fibers of the map of maps to the sims. So one way to compute Euler characteristic when I have a map is to compute the Euler characteristic along the fibers and then push that forward to a constructible function on the base. So I really need to compute the Euler characteristic of the fibers. So the fibers of these things will be like, suppose I just fix the curve support and I look at all the possible things that can happen with fixed curve support. And now what happens is I get some group actions that I didn't have on the whole space. So fibers of the maps to these sims admit some actions. So C star square actions and or E actions. Yeah, so there's two sims here. There's sims involved. Sims. So the maps to the various sims, you can think of it as products of sims, sums over products of sims. So just think, what is that fiber? The fiber just means I'm going to fix the curve support. If I fix the curve support and I look at all possible ways of having thickenings and points, well, I can actually act now on the formal neighborhood of each fiber by a C star squared, and that's going to act on that. So this is a new action that doesn't exist on the moduli space globally, but exists on the strata. Okay, and similar with the E on the components that don't hit the C, I now can act by E. And any sort of thickenings or embeddings, I can look at only those that are invariant. So this is really good news because you can throw out anything that's not fixed. That will have zero Euler characteristics. So throw away everything except fixed points. Fixed loci. Okay, what does that do? In effect, that, when I've thrown everything away, that is going to fix the background thickening along all the curves. And really now all I have to worry about are embedded points. Okay, so then I've got various embedded points flying around. But I can iterate this strategy. I can now stratify by the location of the embedded points. So now re-stratify or find new stratifications on fixed set, and those get new C star actions. And again, these are also parameterized by symmetric products. You can think of this last process here as now nailing down the location of the embedded points. And then in the formal neighborhood of each embedded point, I actually get a full C star cubed action. And I can throw away everything except what's fixed there. So this process reduces me to understanding only subschemes which are formally locally given by monomial ideals. So, in a formal neighborhood of each point, I have coordinates that look like x1, x2, x3, and I can consider just those monomials that are given, those ideals given by monomials. So what it says is that up in that picture, all I've got is the data of where the curves are, where the embedded points are, and then at each point, it's going to be given by a monomial ideal. And now I'm down to something discrete. Up to there's these symmetric products, but then the way that the thickenings happen and the way the embedded points happen is discrete, something I can actually count. So there's one step here, is that the Bryan function at monomial ideals is very simple. turns out to be minus 1 to the n. So that, I've erased the theorem, but that's why I had a minus to the p there. And now we can count monomial ideals using the topological vertex. So I don't think I have time to write the formula that comes out using the vertex, but maybe I'll just say it in words. Topological vertex is a generating function. It's a formal generating function that does exactly this. It counts monomial ideals in 3 variables with fixed asymptotics along the coordinate axes. So it's a combinatorial object. You can think of it as counting boxes in a corner piled up where the boxes are possibly allowed to go to infinity along the corners. It comes up in Donaldson-Thomas theory in the study of toric Calabi-Yau threefolds. But of course, my geometry here is not toric. The lesson here, though, is that by using this motivic strategy, you can import this sort of toric tool. And the topological vertex now appears in a very different way than it does in toric cases. You actually get the topological vertex appearing in the denominator. For the experts here, in the toric case, it never appears in the denominator. And it leads to, and what we get is new identities for the topological vertex that actually make a connection to these Jacobi forms. So the one kind of amazing thing that happens is that various quotients of the topological vertex can be reformulated as operators on Fock space, and they're exactly the same operators that show up in the Bloch-Akunkov Fock representation of GL infinity. So the formulas we get end up being characters of this representation on GL infinity, and Bloch-Akunkov have very nicely computed all those characters, and they come out as Jacobi forms. And this is how Jacobi forms make their appearance in this world with the topological vertex. Thanks for your patience.
So, I don't know, I would again suggest the question we asked partly, since we are running 10 minutes left.
Okay.
That's next.